Hello everyone, I'm Vikram Madduri here. Welcome to Softech, a software architect, and this is part 4 of the machine learning concept that we are discussing. This is a chapter 1, part 4. So in the previous sessions, we were discussing about the machine learning introduction, in which we had discussed about the applications where machine learning can be used. And then we have the data. We discussed about what are the different types of data that we can analyze in machine learning, and the problems or the challenges that we face is what we have discussed. And later we have started off with the probability theory, in which in the previous session I discussed about the random variables and distributions. Now mean and variance is where I was discussing that in the last session. I'll be starting off from mean and variance in this session, and we'll be discussing that, and then we'll be discussing of the marginalization, independence, conditioning, and base rule as well. So let's focus on the mean and variance right now. So I'll take a few of the real-time examples which we come across in our day-to-day life and try to explain what exactly each concept stands out for. So when we discuss about the mean and variance, a common question to ask about a random variable is what its expected value might be. Let's say if we talk about a rabbit, so what would be its life expectancy? The life expectancy in general of a rabbit would be somewhere around say 4 to 8 years. So we are giving a random variable. So if you talk about an instance where we are measuring the voltage of a device, so we might ask what its typical value might be. So we just generally try to take the least and the minimum and the maximum value, and then we'll try to get the mean and the variance through the variance. So when deciding whether to administer a growth hormone to a child, a doctor might ask what a sensible range of height should be. So now then the doctor decides whether it's normal or abnormal. For those purposes, we need to define expectations and related quantities of distribution. For example, if a particular person's age and height would be somewhere around say 20, and his height would be somewhere around 5.10, and what would be his ideal weight. So that is what is the minimum and maximum that we give as a safer path. So that comes under this another example. So for this, we need to have the related quantities for distributions. Now, we'll take a definition. So we can define the mean of a random variable x as t of x is equal to zx dp of x. Remember, this is something which is mean. So when we say mean, we represent it by e of x is equals to zx dp of x. So more generally, if of r mapping to r the function, then f of x is also a random variable. F of x would also be a random variable. It means that it is mean is given by e of f of x is equals to z f of x dp of x. So I'm going to discuss this, and normally I discuss this on the whiteboard as well. So later in coming sessions, maybe I'll be discussing in the whiteboard as well. So e of f of x is equals to z f of x dp of x. This is what we have. I'm going to discuss this again. I'm going to show you that in the diagrammatical way as well. Whenever x is a discrete random variable, the integral in 1.6 can be replaced by a summation. E of x is equals to xxxp of x. So I mean, like for instance, in the case of a dice, we have equal probabilities of one out of 6. For all 6 possibility outcomes, it is easy to see that this translates into a mean of 1 plus 2 plus 3 plus 4 plus 5 plus 6 by 6 is equals to 3.5. Now, let me tell you, if you have not gone through the previous sessions, we were discussing an example of a dice. A dice is something in which we have the probability of there can the dice can have a possibility of 1, 2, 3, 4, 5 and 6, because it has 6 sides. Now when we throw a die, so what would be the probability of getting 2? The probability of getting 2 is 1 plus 2 plus 3 plus 4 plus 5 by 6 is 3.5. So the probability, I mean, like this is something which we normally discuss in a simple concept is what we are taking. So the mean of a random variable is useful in assessing expected losses and benefits. For instance, as a stockbroker, we might be interested in the expected value of our investments in a year's time. So we how do we generalize it? We generalize it by the probabilities of what can happen, and we take into consideration what would be the probability of we getting a loss or what would be the probability of we getting a benefit. In addition to that, however, we also might want to investigate the risk of our investment. This is how likely it is that the value of the investment might deviate from its expectations, since this might be more relevant for our decisions. This means that we need a variable to quantify the risk inherent in a random variable. So one such measure is the variance of a random variable. So when we say a variance, the variance describes what exactly might happen which is not expected. So if let's say I expect the investment today, whatever I have kept would be increased by 30% next year. So what would be the variance that we have to calculate? So one such measure is the variance of a random variable. Definition By definition, what is variance? We define the variance of a random variable x as variance of x is equal to e h of x minus e of x I. As before, if f of r mapping to r is a function, then the variance of f of x is given by variance f of x is equals to e h of f of x minus e f of x into 2i. So this is something which we have to remember. So I'll be again listing out all the formulae, or you can pause this video and write down all the definitions of different variables that we are discussing here. Now, the variance measures how much on average f of x deviates from its expected value. As we shall see in the section 2.1, an upper bound of the variance can be used to give guarantees the probability that f of x will be within of its expected value. So for example, the maximum that my investment would grow is 100%. So there's no way my investment today would be becoming more than 100% next year. So with the maximum, so we'll take into probability the maximum and the minimum values when it comes to the variance. Now, this is one of the reasons why the variance is often associated with the risk of a random variable. Note that often one discusses probable properties of a random variable in terms of its standard deviation, which is defined as the square root of the variance. So the standard deviation would be equal to square root of the variance. I repeat, the standard deviation that we need to remember, this standard deviation is equal to square root of the variance. Now, coming to the marginalization, dependence, conditioning, and Bayes rule. These are the things that we have yet to discuss. So let's discuss what is marginalization. So given two random variables x and y, one can write their joint destiny p of x comma y. Given the joint destiny, one can recover p of x by integrating out y. This operation is called marginalization. So p of x is equal to z by dt xy. So if y is a discrete random variable, then we can replace the integration with the summation. Repeat, if y is a discrete random variable, then we can replace integration with a summation. Now, p of x is equals to x, y, p of xy. So we say that x and y are independent, that is, values that x takes does not depend on the values of y takes whenever p of xy is equals to p of x, p of y. So independence is useful when it comes to dealing with large numbers of random variables whose behavior we want to estimate jointly. So for instance, whenever we perform repeated measurements of a quantity, such as when we use a sample from two dependent random variables. So knowing about first coordinate allows us to improve our guess about the second coordinate. So uh, a simple, in the right side, if we see a sample drawn from two independent random variables, wherein like obtained by randomly permitting the dependent samples. So these are the two examples in which, so in the diagram we are taking up examples where we have the dependency on of x on y, and there is in the x and y values are independent. I'm going to come back to this diagram and explain it more clearly again. So we'll take example of when we are repeatedly measuring the voltage of a device. When we are regularly doing it, we will typically assume that the individual measurements are drawn from the same distribution, that they are independent of each other. So what exactly it means is your past voltage of the device need not be dependent on the next measurement of the voltage. So the next output will be completely independent of the previous output. So that is, having measured the voltage a number of times will not affect the value of the next measurement. We will call such random variables to be independently and identically distributed, or in short, IID random variables. So no matter how many times we iterate the process, still the next value is independent of the previous values. And we are going to discuss that in the figure, for example, of a pair of random variables drawn from dependent and independent distributions respectively. So that's what we have here. So basically, if we have independent, we have dependent objects, we have a different kind of estimate. When we have the independent objects, we have a different kind of estimate. Conversely, dependence can be vital in classifications and regression problems. For instance, the traffic lights at an intersection are dependent on each other. This allows a driver to perform the inference that when the lights are green in this direction, there will be no traffic crossing his path. That is, the other lights will indeed be red. Likewise, whenever we are given a picture x of a digit, we hope that there will be dependence between x and its label y. These are the kind of dependencies that we have. So there is a dependency so the signal, the first example is, imagine that you are at a signal and you are seeing a green light, and it's taken for granted that the crossing line would definitely be on red. That's something which is interdependent. Okay, so one output is dependent on the other one. Likewise, whenever we take a picture of x of a digit, we hope that there will be a dependency between x and its label y. So this is another example, random example. So we take that x and y, especially in the case of dependent random variables, where we are discussing about the dependent random variables. We are interested in conditional probabilities, that is, probability that x takes on a particular value given the value of y. So clearly, PR of x is equals to rain, y is equals to cloudy. Is higher than PR of x is equals to rain, y is equals to sunny. So in other words, knowledge about the value of y significantly influences the distribution of x. This is captured via the conditional probabilities. Px of y is equals to Pxy Py. So in this equation leads to 1.14 equation leads to one of the key tools in statistical inference. So theorem 1.5 of Bayes' rule denote by x and y random variables, then the following hold: sp y of x is equals to px of y, p of y, p of x. So this follows from the fact that p of xy is equals to px of y, and py is equals to py of x, x. So this is some equation we need to make a note.